Last question of Statistical Rethinking, second edition, easy questions for chapter 5, so 5e4. So I'll let you read the question here and I'll kind of describe it in my own words. So we have a data set that includes a categorical variable, and that categorical variable can take on one of four values, A, B, C, or D. So we can think about this as color of shirts of people on the street. And it could be red, yellow, green, blue, or something like that. That's what a categorical variable is. So when a particular data point is of category A, then that data point, A sub I representing that individual data point, will equal 1. But if that data point is not A, or is not, if that data point is not A, then that value in the regression would be 0. And similarly for all of the other categories, B, C, D. Okay. So in other words, it's as though we were on the street and we were marking off people's color of shirt, and assuming that all shirts are just a solid color. If it's yellow, then it certainly isn't red, and it's not green, and it's not blue. Okay, so that's what's going on. So in any one of these regressions, the idea is that the data will have only one of the terms equal 1, and the rest will equal 0. Okay, so this is a common way of kind of encoding categorical data. It's not the only way, as we'll see later, but that's okay. It works, and that's what we are doing here. So what we were asked to do is to look through these 5 different regressions and say which ones are equivalent. Okay, and what is meant by, what does it mean for two regressions to be equivalent, right? We see that these are, I mean, just a cursory glance says that these are not the same, right? They have different terms or different lengths, etc. But it means that we could deduce the posteriors for. So we could deduce the posteriors for the beta A and the beta B and the beta C and the beta D, or whatever, or the effect of A and the effect of B and the effect of C and the effect of D on mu I. We could deduce those values of one, say, of this regression from the other regression, right? So in other words, we could take the posterior of regression 1. And could we or could we not find the same, or find the posterior for regression 3 without running the calculations through 3? So are they interconvertible or not? Okay. So let's start here with 1. Obviously 1 is common to itself, but let's just establish what's happening here. So in 1, we see a term for every category, or except for C. We have A, B, and then no D. And so the first thing to notice is, or the first thing that we might want to think is, okay, well, maybe 1 doesn't work. It doesn't model all of the different categories, right? We're missing Z. But that's not exactly right, okay? So remember that our intercept, if we have a single intercept, that is the value of mu in this case, when all other variables, all other explanatory variables are 0. So if A is 0 and B is 0 and D is 0, so in other words, it's not category A, it's not category B, it's not category D, assuming that every data point is either A, B, C, or D, then that means that alpha actually represents the effect of C on mu. So alpha in this case would be similar to beta C, Ci, right? Okay. So now let's go down to 2, and we see that 2 is longer than A, or is longer than 1, because it has the C term in here, right? But it also has this intercept. And so there's actually more parameters here than are in 1, okay? And so what alpha would represent here is the average effect of each category on mu. And so all of a sudden we're estimating an additional parameter, and so the beta A and the beta B and the beta C, etc., will not be the same as the beta A and beta B and beta D found in regression. So 1 and 2 are not equivalent. Okay. So now we go down to 3. Okay, and we see that this looks very, very similar to 1, except this one has C but omits A, right? So 1 has a beta A term, 3 does not. 3 has a beta C term, 1 does not. Okay. So by the same reasoning that we realized that 1, even though it was missing a term for C, was still could still adequately represent the data, so does 3. But now alpha here represents the beta A term, okay, and it has a beta C term, right? So in other words, if I had the posterior to this distribution, I could equate that to the posterior distribution of A, or to 1, right? It would just be that the beta A term would be equivalent to the alpha term here in 3, okay? And the alpha term in 1 would be equivalent to the beta C term in regression 3. So 1 and 3 are equivalent. 2 is so far the outlier. Okay. Number 4. So this has a, well, okay, so first of all, we see that there's a term for every category, and there's not an additional term here. So we have 4 terms, one for each category. Okay. The next thing that I notice is that we have alpha terms here. And is that a problem? So whereas in the other regressions we've been using this beta term as the slope, as the coefficient for the data, here we have alpha. And the answer is that this is not a problem. This is just, the symbolism that we tend to use, that is being used in this regression, right? Generally, what is going on is that the beta term is a slope, and so that would be more common to see here. And alpha is reserved for intercept, but just because we plug a different symbol in here doesn't really, it is of no significance. Also, we will later see that sometimes interactions are portrayed in a similar way. So this might not even be all that anomalous. But now the next thing is this equivalent to 1 and 3, or is it equivalent to 2, or equivalent to neither? So again, we can estimate each one of these terms, and each of these terms could line up with the same, or with a term in both regressions 1 and 3, right? So in regression 3, this term would give us the value, would give us the effect of A on mu when all of the terms are 0, and in 3, that term happens to be the alpha term, just the intercept. The B's would be the same, the C's would be the same, and the D's would be the same. And then we can apply that same logic to 1. So 3 is equivalent to 4, 4 is equivalent to 3, and 3 is equivalent to 1. So 1 and 3 and 4 are all equivalent. 2 is still the outlier. Okay, final one. So we have mu being equal to this big thing. Okay. So again, we see that we're using alpha terms, but that's as kind of the slope coefficients here, but that's of no consequence. That's fine. We see that there is one of these Greek letters for each term, A, B, C, D, just as there was in 4, and we said that 4 was equivalent to 1 and 3. But the coefficient for A is multiplying this monstrosity here. And so this looks a little bit weird, and so we need to think our way through this. So again, ultimately what we want this term to be is either 0, right, because the data point is not A, or we want it to be 1 times the coefficient, right, if it is A. So when I look at this, so what happens when the data point is actually A? Well, then we have alpha 1 or alpha A times 1, but that would mean that BI, CI, and DI are all 0, right? Because the data point is A, so that means it's not B, C, or D. Now let's say that the data point is not A, it is either B or C or D. Okay. Well, now we have alpha A times 1, so it's alpha A, but then one of these B, C, or D is going to be 1. So that means that this whole parenthetical term is going to be 0, which means that this term is 0, right? And that's exactly what we want for our categorical variable, right? So this right here is akin to just having AI in there. Okay, that is it.